Building a satellite is no small feat. Decades of experience and hundreds of missions have shown us that space is an unforgiving environment. Once a satellite is launched, there is no turning back. Every scenario must be accounted for. But what exactly does it take to design a satellite? Let's find out as we zoom in on the YP-SAT, a satellite engineered by young professionals at the European Space Agency. The complex task of capturing footage of key moments from Ariane 6's inaugural flight calls for the need of different subsystems making up the satellite. To achieve the mission objectives, these systems must work in harmony and follow a predefined mission sequence. Join us as each team delves into their own intricate subsystems that make YP-SAT's voyage into space possible. First, let's look into the wake-up system, also known as WUS. Running at ultra-low power, this circuit board was designed, tested, and manufactured especially for this mission. It was created to meet Arianespace's requirement that the YP-SAT remain operational on the launch pad for up to 45 days. Its purpose is to detect the launch and turn on the rest of the subsystems.
It's definitely special because it's active during the launch. Usual payloads only get woken up when the launch vehicle is in orbit. But we want to record before that happens because we want to catch the fairing separation.
And for this, there is no off-the-shelf solution because nobody wants their satellite to be turned on the pad for 45 days. So we came up to a solution that, okay, a circuit board, it needs to be super safe. So we have one microcontroller, but all of the sensors are there 3 times. We have 3 barometric, so pressure sensor. We have 3 accelerometer, and we make decision based on all 3 of them to make sure that even if one of them fails for whatever reason, we can continue.
So we're just sitting there on the launch pad, and as soon as we get shaken, we detect, oh, there is probably a launch happening, but it could also just be that the fairing is closed and there was a shock. So how we detect that? We read out the pressure sensor, because when we actually launch up, the pressure drops, and after a bit more than half a minute, the pressure will drop to 0.5 bars, and then it will wake up the system. So if you want to have footage of the fairing separation, then this board better works.
So yeah, the first version was a proof of concept, and then we could move on to a second circuit board, which then we decided to test in the balloon launch. And through networking of ESA, I understand, we discovered that there was a stratospheric balloon launch experiment launching from Budapest. It did most of the things we wanted. Not as fast, but the concept was good. So at first it's on the ground, static, nothing's happening. And then suddenly there is an acceleration upwards, and then there is the atmosphere getting thinner and thinner as we go up. So it was a very good analog simulation of the launch, except the values, like the exact acceleration, the exact rate of change of the atmosphere was different. But that is just a parameter to change in the code. We wanted to test our logic. And it was a complete success. We're super happy about it. I'm really proud that there will be one of my circuit boards on Ariane 6. After the mission is done, it will burn in a gigantic fire, and that's going to be awesome.
Once the WUS detects the launch, it will signal to the battery to turn on the rest of the satellite, something the WUS cannot do on its own. The challenge is for the battery to maintain enough charge to power the remainder of the mission.
That's why we just left the satellite as it would be on the launch pad, and we were constantly monitoring what's the state of the battery. And this way we can have a very good view over time of how does this battery behave while it is being used during the mission.
The battery, they have a few major accidents. I think the first time that they test the battery, it didn't survive the vibration. The second time there was an accident integrating the battery. The third time it was something related to the voltage of the cells, they were unbalanced.
So we were seeing behaviors that are not normal and that show that the battery is not healthy, so it might be dangerous. Because you have 4 cells in series, and as there is no balancing circuit, they were not all at the same voltage, for example. This means that they are unbalanced.
At that moment, it was a bit of a crisis situation for the project because there was this high risk from these initial results that we might not have been allowed to fly.
We found out that the current that was out of the battery was quite high, so we thought maybe that's a reason for the unbalancing or the unhealthy battery.
So we had to change it. And while it's being changed and repaired, we are making here a test of a new circuit that we put between the battery and the power distribution module to dampen this very high current that we get at the beginning.
One of the nice things of this is that they have developed this in record time. 1 month ago, we knew that there was this problem, and then quickly they team up, they split the tasks in functions, and they came up with a simple idea, which is a soft start based on an inductor and input capacitance. Yeah, I'm very happy.
Now we are very happy with the solution. It's protecting even much more than we expected. But it's just the test on one part of the satellite, so now we have to try with the battery and the rest of the satellite so that we are sure that everything will work well and the battery will not lose more energy.
With the satellite now powered on, the onboard computer takes the lead to orchestrate the rest of the mission. The OBC acts as the brain of the operation, sending commands to all the other subsystems.
We are responsible for making sure that we take images at the correct time, making sure that we start collecting data with different instruments when it's time, and we also offload the data from the instruments to the transmitter so we can downlink it to the Earth. Without us functioning properly, there will be no mission, really. So it's important. I can show you, I have the engineering model. This is a tiny computer. Inside is a microcontroller, and it has a bunch of interfaces to work with the other parts of the spacecraft. So on the sides there are a lot of different connectors that you can use to connect to solar panels, and you can use to connect to camera. There's onboard storage in here. You also get power and communications buses that you can use to talk to the different systems. And this is a commercial off-the-shelf part, so there's a lot of features that we are not using. For example, we don't have solar panels on the YP-SAT, so we don't need those connectors. But it's a very good starting point, and it's a way to quickly and cheaply put together a space mission.
With the footage captured and stored, the OBC will dispatch its last order for the antenna to continuously beam the data back to Earth. The telecommunications team then takes over in coordinating with the ground stations to capture the data so it can be decoded into clear images.
So there's a big telecommunications group. We have the people really working on the decoding side of the data, but we also have the ground station group in contact with the ground stations to actually receive that data. And then we have mission analysis, who analyze the visibility window and the downlink window of potential ground stations that we want to collaborate with. So we need a few inputs in order to know if a ground station is useful for us. So one of the inputs we have is we have a simulated trajectory of Ariane 6, but we also need to know some characteristics of their antenna to make sure that the signal is actually strong enough to retrieve the data. If there is a collaboration, so if we do have that visibility window, We have to provide tracking files leading up to the launch to make sure that the ground station can actually point in the right direction to follow YPSat.
A ground station is a combination of systems, which includes also an antenna, that we need to downlink the data from our satellite. We have some constraints from the launcher side on the frequency and power that we can use because we stay attached to the launcher. So we chose an antenna that is in S-band, and most people would say that's amazing because we are full of S-band stations on ground, but the trick is we are not normal S-band, we are amateur S-band, we're not commercial, so we cannot just go to normal operators and request to use their ground station. On the other hand, we have a very limited power on board, so we need to compensate that with the ground system, so we need to have a big infrastructure, but for amateur people. So it's the combination of two very challenging things. I remember Julia telling me, you have to build your own ground station. And I was like, okay, no problem. But inside I was like, I don't know how to build a ground station. So yeah, together we were trying to figure out how to buy or reuse parts of ground stations that we already have at Esrin. But then we saw there was a huge wave of people wanting to help that we didn't need it at the end, but those were hard weeks where I was trying to figure out how to build our ground station.
Mostly in Europe we have found some ground stations that can help us, but we also fly over Australia and the north of South America. But having them concentrated in Europe also means we have some overlap. So maybe one station is not able to retrieve our data, then maybe we have another chance with another ground station at the same time.
So as you can see on the YPSat, we have only one antenna. But obviously when the launcher is always rotating, this antenna isn't always pointing towards the Earth. So that's why we implemented a specific downlink strategy to really make sure that we downlink our data several times during one rotation.
The downlink strategy is the way that we hope to recover the data on Earth. So this downlink strategy takes into account the data from mission analysis, mainly the downlink windows and the data rate, which was also verified with these equipments. This machine, the NewTek decoders, allows us to decode the signals, the DVB-S2 signals, and demodulate, of course. And then we have connected to this module our own program, the image and video recovery program that allows us to quickly recover the images and videos.
The recovery of these historic images would be a testament to the hard work and dedication the YPSat team has demonstrated over the last 3 years. Their dream hinges on every bolt, screw, line of code and piece of hardware working in harmony. However, there is one more hill to climb before the YPSat is launched. The team will assemble the YPSat for the last time and subject it to rigorous tests, from vibration and temperature extremes to vacuum conditions and electromagnetic compatibility. Each element must meet the stringent standards of the European Space Agency and Arianespace. Will YPSat accomplish its mission objective? We'll find out in the next episode.